Good morning, ladies and gentlemen. Today will be a much quicker video than yesterday's video, but I want to start out by saying thank you to those of you who are answering the questions, your peers' questions on the question stream for each problem. I went through and I sort of looked at the questions that were posted and also the questions that were answered and how they were answered, and it's looking great. Honestly, all of you are spot on. And also thank you to those of you that are asking questions, because you're asking a lot of the really important concepts that students typically struggle with. So keep that up, right? We have 2 weeks to go. Let's stay strong now. And once these 2 weeks are up, it'll be all worth it. All right. So again, thanks a lot. Let's keep going. All right. So I'm just going to go over one part from the first problem and one part from the second problem. So for problem number 3, again, we're given a table of values. In this case, though, we're given the function C, which represents the actual amount of coffee in the cup at any given time t. Now, in this situation, we're only given a few snapshots of the amount of coffee in the cup, and that's what the table of values gives us. We're also told that this function C is differentiable, which also implies continuity on this interval. All right, and today we're going to look at part B. So it's saying, is there a time t at which C prime of t is equal to 2 on this particular interval? So what I've done is I've taken this snapshot, I've taken these 7 points, and I've plotted them on a graph. All right, so when we look at the amount of coffee in the cup with respect to time, we have this red curve here. Part B asks us to look only at t equals 2 to t equals 4. And it's saying, is there a rate of change, an instantaneous rate of change on this interval that is equal to 2 ounces per minute? So is there any instant such that the instantaneous rate of change is equal to 2 ounces per minute? Well, in order to answer a question like this with such a limited amount of information, we're going to have to rely on the mean value theorem. The mean value theorem says that as long as you have a function that is continuous and differentiable on an interval, and also there is a secant line slope that is equal to some particular value, then there must be an instantaneous slope or tangent line slope that is equal to that value. All right. So a secant line slope tells us an average rate of change, right? A tangent line slope tells us an instantaneous rate of change. So essentially, a way you can think of the secant line slope is it's sort of like an accumulation of all of the tangent line slopes, and then we're dividing by the length of that interval, which in this case is 2. You know it from pre-calculus is just sort of change in y over change in x over this particular interval. So anyway, taking the 2 endpoints, we have the point 2, 8.8 and 4, 12.8. We're just simply going to use those 2 points and find the slope. We end up getting 2 ounces per minute. That's the slope of this little blue line right here. All right, but what this tells us, coupled with the fact that C of t is continuous and differentiable, it tells us that somewhere along this curve here, there's going to be an instantaneous rate of change that is equal to 2. And that's the mean value theorem. Okay, and this is essentially the argument you would make. Since C of t is differentiable on 2 4, and also therefore continuous on 2 to 4 inclusive. And since the average rate of change of this function on this interval is 2, then there must exist C prime of t equal to 2 by the mean value theorem. Now I'm just going to actually make an adjustment and include the units. All right, this would be a complete argument that you would have to make. And actually, I'm going to pause for a moment and I'm going to create something a little bit more visual so that you can get a better understanding. So just give me one moment. All right, back to this explanation of the mean value theorem. What you're looking at is a diagram of a graph, the blue curve. You're looking at a secant line, the black line segment, and you're looking at a tangent line, the red line. Now again, the mean value theorem says that if a function is continuous and differentiable, as the blue curve is on this interval, and if there's a secant line that has a particular slope, then somewhere along this interval there will be a tangent line that has the same slope as the secant line. Now, at this moment, you could see the tangent line and the secant line do not have the same slope, but as I adjust the point location, you can see that the tangent line slope is changing as x changes, and from some point between 2 and 4, there definitely seems to be a point where the tangent line is parallel to the secant line, and that would be the value that satisfies the mean value theorem. But the mean value theorem guarantees us the location that there does exist some point where the tangent line and the secant line have the same slope. All right, so this is just sort of a visual illustration of that. Okay, hopefully that helped a little bit. All right. So anyway, that's the mean value theorem. And for this problem with the water temperature, I wanted to discuss part D. Part D, this is a type of problem that I almost guarantee will be on the AP exam, where you're given a rate, you're also given some, you're asked for, in this case, the amount of water at t equals 25. You're given the rate of change of water from t equals 20 to t equals 25. And you also have other information that tells you the amount of water at t equals 20. So this is that formula that we've seen time and time again, where the value of a function at a later point or even an earlier point is equal to the initial condition plus the integral of the rate. More specifically, if we want W of 25, we'll take this known piece of information as sort of like an anchor point, and we'll integrate the rate of change of water temperature from t equals 20 to t equals 25. Once again, this integral represents the net change in temp from t equals 20 to t equals 25. So if we know the water temperature at 20, and we also know the net change in temperature from 20 to 25, we can use that information. In fact, we can add those two pieces of information together to get the water temperature at 25. So W25 is going to equal 71 plus, now this is not an integral that you should be able to do by hand. And so I strongly recommend that you use a calculator, because, well, if you don't use a calculator, you're just not going to be able to evaluate this integral. We haven't learned any of the methods required to evaluate this integral. And as you can clearly see up here, a graphing calculator is required for these problems. So the AP is not expecting you to evaluate this integral by hand. Use the function on your calculator that evaluates definite integrals. You would see that the definite integral stated here ends up being 2.043. What that means is from t equals 20 to t equals 25, the water temperature changed or increased by 2.043 degrees Fahrenheit. All right, and so at this time, the water temperature is 73.043 degrees Fahrenheit. All right, folks, that's going to be all for today. Keep asking those questions and keep answering those questions. I got to say, you're doing a really great job. I'm very, very pleased with what I see. Keep it up, folks. We're almost there. All right, take care.